Good evening. Welcome to Kopernik Observatory. It's great to see you all here this evening. It's morning somewhere, just not here, I guess. My name is Drew Desker. I'm the director here at Kopernik, and very happy to see a nice crowd here. A show of hands, who's here for the first time? All right, about half. And okay, by show of hands, who here is a member? All right, yeah, the other half. All right, great. Well, what I always like to do is point out the particularly valuable piece of information the people who raise their hand second have is that of a Kopernik membership. Kopernik we're a nonprofit, but we belong to what's called a consortium of other nonprofits called the ASTC, Association of Science and Technology Centers. And we all honor each other's memberships. So you can take your Kopernik membership card, you could go to Roberson Museum, you could go to the Ithaca Science Center, you could go to the Museum of Science and Technology up in Syracuse, or the Intrepid down in New York City, or the Franklin Institute down in Philly. And very often you'll find that if you were just to go there with you and your family, you'd be paying more for that one day's admission than you would for a full year's admission with a Kopernik membership. So if you like this kind of place, and as maybe if this summer you plan to do some traveling, you might want to consider investing in a. And I think I lost my mic. I guess I didn't. So we just finished celebrating our 50th anniversary of being a public observatory and informal STEM education center. And so a little bit of a background here. We opened actually in 1974, and besides being an observatory that people can come up here on a weekly basis, we also do a lot of outreach to schools. This past couple of weeks, we've had a number of first grade classes coming through here. For those of you that are here, if you look around, you can see a bunch of telescopes in the back. We actually had a telescope petting zoo for first grade classes. We're also now doing, we're well into our registration for our summer camps. This is our 33rd year that we've offered STEM summer camps for students as young as going into second grade, current first graders going into second grade, all the way up through high school. And so information on that you can always find on our website. So if you went over here to classes, events and programs, you go to public classes, summer camps, you'll find out what we're offering. And a number of these camps are actually pretty close to being sold out, actually are sold out. But we still have a number of spots remaining in some of our camps. And so if you know of a child or a grandchild that might be interested, these are day camps that we really focus a lot on hands-on, have a lot of fun. And what's also great is that you get other kids that are really interested in science and engineering, that you get to make some great friends. But tonight we're doing one of our regular Friday night programs. So every Friday night between March and mid-December, we always offer some public program of on some topic, not always about astronomy. And what we do now also is we live stream them. Back in 2020, when we had to stop for COVID, we started live streaming our programs, and they became so popular that we continue to do that. And so we also want to welcome those watching on the live stream this evening. We now have, we're closing in on 14,000 subscribers. And so we actually have a YouTube channel that you can go to. If you go to YouTube and go to Kopernik Observatory and Science Center, you can watch us like people are doing this evening, watching us live. But what's great about the channel is that all of our live streams are recorded, and you can go back to it. So last week, actually 2 weeks ago, we had a talk on AI for all. The previous week before that, we were talking about the Fermi paradox, the Venus and Lucifer. We also had on Pi Day, we had a game of paradox and the most irrational number. But beyond our Friday night programs, we also do programs when we offer live streams when there are particular astronomical events going on. In fact, if you recall, back in March, there was a lunar eclipse. And so Jenny, our live stream astronomer driving the live stream here this evening, was up here for 5 hours doing a full live stream of the lunar eclipse, and actually put this nice little 1-minute compilation together of the eclipse. So let's take a quick look at that. Now, again, this happened over about a 2.5-hour period of time. It didn't happen this quickly. It's clearly a time lapse. And she changed the exposure so that we could thank you. And so for those of you who have a little bit of astronomy and telescope knowledge, this was all done with a C-star, basically an automated telescope that is actually not one you look through, but it actually communicates to a computer or a tablet. So, anyway, so definitely check out our YouTube channel for previous programs. But again, one of the things I really enjoy about being up here are these Friday night programs. It's actually an opportunity for us to expand our knowledge about the world. And in particular, I like, especially with for the younger people that are here, your education doesn't end in 12th grade or at the end of college. It's really meant to be a lifelong pursuit. And as I always like to say, well, for me, I really wish I could live another 50 or 100 years just to see where is technology going to take us? Where's engineering? Where's medicine going to take us? I mean, when I was your age, I used to have to walk to the TV to change the channel. Well, and we only had 3 channels back then when I was 11. So where are things going to go now? And these kind of programs are really an opportunity for us to find out what's going on in the world and allow us to maybe pursue some new interest. Again, we're very fortunate here in the area to have some extraordinary schools of higher education. Binghamton University, of course, is very close to us, and we've had many of those educators come here to talk. But just right up Route 96, is that the way you came down, or 38? Which? 38, 79. Depends on where you're starting from. Cornell University, nice little school up the road here, has an extraordinary astronomy department. If you remember Carl Sagan, that's where he taught. And well, we were very fortunate that Zoe Luna Ponterio is from the Spacecraft imaging. Well, I always get this wrong, so I won't even start. But anyway, we're very fortunate that Zoe is what she does is outreach for Cornell, and I'm looking forward to tonight's talk. So I'm going to just stop rambling on and turn it over to you, Zoe. So let me also get her computer plugged in here. So hold on one.
All right, how is my mic? All right, great. So yes, thank you, Drew, for inviting me back up here again. The facility that I run is SPIF, the Spacecraft Planetary Image Facility. So we are both a public facility and a research facility, so people will come visit. I'll go on the road to make presentations, but also I have students and researchers there that come to me who need help finding the images they need that were taken by spacecraft to do their research, to work on their class projects, and also help them learn how to use different software to process those images and analyze them. My particular specialty is in mapping, so I teach people how to use programs to map other worlds that were very much designed with Earth in mind, So it's a fun endeavor to sit there and work with something that clearly someone was thinking of Earth, but we're going to use it on other worlds, some of which are not even round, which gets very interesting if you try and think of latitude and longitude on an object that is not round. So I've come tonight to give a talk that's a little different than any talk I've ever given here. And that is because this is going to be a talk where we're going to start from the very smallest things, and we're going to build all the way up to the very biggest things. And we're really not going to talk a lot about anything in between, which is kind of where my jam is, right? I'm all about solar system, planets, life forms, rocks. We're totally going to skip over that range of sizes tonight and do something different. So you can contact me if you want to come and visit SPIF. I have a meteorite collection, a lot of archival photos and cameras and things like that, and a lot of fun hands-on activity, including Martian virtual reality. This was something developed by people in my group, a graduate and undergraduate student. They are the real images taken by the Perseverance rover, built into a fully immersive VR experience, so you can literally sit there and see exactly what the rover saw at about a dozen different sites on Mars. All right, so let's just dive into this and start with the small stuff. So we're going to kind of get a crash course in quantum mechanics here. So don't worry, don't run off. It's going to be fine. So what is quantum? We hear that word a lot. In fact, if you're a Marvel fan, you wonder, do you guys just put the word quantum in front of everything? And their answer, of course, is yes. Yes, we do. But what is that really? A lot of times people say quantum and they automatically think small. And while it's true that small things are what quantum mechanics helps to describe, we can actually see quantum behavior in things that are everyday experiences, like a string of Christmas lights. So these lights represent two different ways of measuring something. You could measure the length of the cord. And everything's going to be a little different. They're going to vary in, if like you can stretch it tight or you can have it kind of loose. So there's a range of measurements you might get for how long that string of lights is. That's a continuous variable, right? It can take on any value. You can move it back and forth, it's fine. But if I ask you how many lights are on that strand, that has a very fixed number. That has to be a whole number. You're not allowed to have half a light on there, right? And you can't be in between lights and say, I'm sort of a light. You either are a light or you aren't, and that is a very fixed number. That is what it means to be quantum. So some other examples here. My kids at least played with something, even with a light bright, but I don't know if any of the other kids have ever done it, but I'm sure some of the grown-ups in here. Light bright is where you put little punches of different colors. There's a light behind it, and you can build up a picture. If you zoom in on a digital picture, it has pixels. You've seen this. That is what mathematicians call discrete. Again, it has a fixed whole number count. As opposed to an Etch-a-Sketch, or actually just drawing on a piece of paper, where you are just continuously making drawings. So again, we would call the light bright quantized. So that is what quantum means. It means things that are specific values and you're not allowed to kind of be sort of or halfway. It either is this or this and nothing in between. So now we're going to talk a little bit about the structure of an atom, and we're going to start historically way back in the 5th century BC, where Democritus was the first, that we know of at least, to propose that matter was made of very, very tiny things you couldn't see, but that there was a limit. You could keep on chopping things up smaller and smaller, but at some point you would get to a piece where you could not chop any further. And yeah, he was right. So then we're going to fast forward all the way to 1803. John Dalton proposes that atoms are invisible to our eyes, and that different elements are formed by different kinds of atoms. Okay, really basic idea to that. 1897, J.J. Thomson says, well, the atom is spherical, and there's positive and negative charge in there somehow, but we're not really sure how. Okay, kind of like maybe a cloud. And so this was the thinking when along comes Ernest Rutherford and does an experiment that is honestly one of my favorite experimental experiences historically, in which, assuming that Thomson was right and it was a cloud of positive and negative charge just kind of in this cloud, he's like, I bet I could find out what the structure of that cloud was. If I take these things called alpha particles, we don't know what they are, but they're super tiny but really dense, like tiny little bullets. They're smaller than atoms. So if I shoot these alpha particles at a thin sheet of gold, they'll go through that atom cloud. And because alpha particles are charged, they're positively charged, and they pass through the positive and negative charges, they'll get nudged a little bit. You know, tiny little bit. And by looking at how those alpha particles then were detected on the other side of that gold foil, they might be able to get an idea of what the internal structure of an atom was. So they turned on the machine, and for the most part, everything seemed to be working, except that most of them just seemed to be going straight through. But then they noticed something even stranger. Some of them were going like way off at an extreme angle, and some of them were missing entirely. Like, where did the alpha particles go? There was a certain number of them that just weren't showing up until they extended the detector all the way around behind to find that some of the alpha particles were hitting the foil and bouncing straight back. To understand how shocking this was, he compared it to firing a gun at a piece of tissue paper and having the bullet bounce back at you. Of course, what he discovered was actually that it's not a cloud. There is a tiny positively charged nucleus. Hey, come to find out, those alpha particles are nuclei. So that's why the bullets were bouncing off. Every once in a while, one would hit an equally dense nucleus and bounce off, but the electrons were particles that were circling around that nucleus. Okay, we're getting there, we're getting closer. Then we get to 1913, just a couple of years later, Niels Bohr figures out that the electrons aren't just kind of going anywhere. They have a very specific pattern. They have shells, he called them. So when you're close in, that's a very low energy shell, and you can move up, that's a higher energy shell, because you require energy to push a negative and positive charge apart, right? They want to be together. So this is called the planetary model. We imagine these electrons orbiting around the nucleus in specific shells. And this is the beginning of realizing that it's quantized, right? That those electrons cannot just be any old place around the atom, that there are fixed shells that they must exist in. And they can move from one shell to the other, but somehow they don't exist moving in between. They seem to wink out of existence of one shell and show up simultaneously in another shell. Still not sure how that works, but okay. So the simplest example of this we can think of is hydrogen. One proton at the center, and then an electron around there, and here are three of the innermost energy levels, shells that electron could be in, 1n, 2n, 3n, and so on. And so we also know that these particles are quantized. That means a proton has a fixed positive charge, and every single proton has exactly that same charge. And the electron has an equivalent but opposite negative charge, and every single electron has that exact charge. So you're not allowed to have any old charge you want. Charge is quantized. And so a question I often get asked is, what if there's elements on the periodic table that we haven't found yet? Or in movies and TV shows, you'll hear like, oh, whatever this is, it's not on the periodic table. Marvel, again, did that one in Captain Marvel. No. This is all of the elements, at least below, where'd we go up to? 118. It's quantized. You can't have 1.5 protons in your nucleus. So that's why, no, these are all the elements that we run into in everyday life, and several heavier ones that we can only make in laboratories. That being said, there are some people that think that there could be some even further down enormous atoms that might be naturally stable. Because for the most part, you get down to these really huge ones with 100 protons in their nucleus, and you can make but they fall apart really quick because you're just trying to stuff so much into that nucleus. But yeah, we don't have any elements in that range that we haven't found. That's all of them because of quantized charge. And And that's a really nice story I just told. But you'll notice that there is still a missing panel here, because Edwin Schrödinger, yes, of the famous cat Alive or Dead, in 1926 realized that, yeah, the electrons are kind of in a cloud around the nucleus. And you're like, wait a second, I thought we got over this cloud thing. I thought you said, no, it's not a cloud. Now we're back to cloud? But then how can it be quantized if it's a cloud? All right, so this gets a little hard to picture, because asking how a cloud can also be specific particles of electrons and they're quantized, what does that mean? Well, it's more like a big ball of wibbly wobbly, cloudy electron-y stuff. Any Doctor Who fans got that joke? Yeah, this is kind of the picture that starts to come out of this, that at the center there is this very prominent nucleus, but that the electrons, being much, much smaller than the protons and neutrons of the nucleus, kind of exist in a number of different places at once. This is where it gets a little tricky, and we're not going to dive too deep into these weeds, don't worry. But yes, you cannot know where the electron is at any given moment, but we can say where it's likely to be. And so instead of Bohr's shells, we now have Schrödinger's orbitals. And yeah, we're right back to using orbits in the planetary model, which is what Bohr said, but no, we're not using that. All right, now, they have different orbitals, the s orbitals, right? You're close in, that's a low energy because you don't have a lot to separate you from your nucleus, and as you add more and more energy, your electron can venture farther away from the nucleus. And this is kind of like, okay, all right, so there's these clouds and the electron's somewhere in there, right? There's places where it's more likely to be, less likely to be, and we're doing fine. But then there's orbitals. The next is the p orbitals that have clouds that are shaped like two lobes and then two little lobes within lobes. And then you've got the d shells, which start looking kind of like two balloons with a, you know what, I know the fuzziness looks a little weird, right? So maybe this will make it clearer. Okay, so this is the S, the P, and the D, and the F shells, and the shapes that the orbitals take. Okay, how about we just forget that, and we'll go back to this. All right, we don't need to worry ourselves about that. If that just piqued your interest, then you want to dig into quantum. If that just kind of made you go, what, then just forget you ever saw it. All right, so back to hydrogen, simple case. The electron can be in one of those shells, and it must be in one, and somehow it can move between shells despite the fact that it can't exist except in a shell. All right, we're just going to have to accept that this happens for now. All right, so now we get to talk about that process of the electron changing shells, which is referred to excitation and de-excitation. So yes, electrons get excited, and then they get bummed out. So electrons can absorb energy in the form of light. So if a wave of light comes in, the electron can absorb that light if the light has just the exact right energy that the electron needs to jump to the next shell. Only if it has that exact energy. But then it doesn't stay there because, again, positive and negative want to come together, and at some point the electron falls back down to a lower shell, but energy and mass are conserved, so it has to give up light with that exact same energy as it falls back down. And this can happen over and over and over again. This diagram gets a little more complicated, but the thing I like about the diagram is right here, this one, that shows it as like a ball falling down steps, because I think this is the best way to think about it if you don't want to dive too deep into the quantum mechanics of it. A ball on stairs is an example of being quantized. Now, in truth, yes, there's a moment where the ball exists between stairs, but it can't just hang out there, right? The ball has to be on one of the stairs. And if you go in with your body and you spend calories and lift that ball up to a higher step, you have put energy in and you've put exactly the amount needed to get it to the next step. You're not going to sit there halfway between step and drop it. Don't be like that. So you're going to place it just right on that step. You have excited the ball up the stairs. But eventually, you know, the ball's going to wander around and it's going to roll back down the stairs. And when it rolls down and hits the next step down, it releases energy in the form of sound. Except our stairway is not all even steps, right? Those energies of those shells are not evenly spaced. In fact, it tends to be the biggest step is getting out from the bottom shell, and then the steps get smaller and smaller as you go there. So that means in this case, the ball is going to hit with more energy if it falls farther. So if it goes down a small step, it's going to make a little noise. If it falls down a big step, it's going to make a loud noise. So energy in, energy out. Now at this point, this gets a little funky because you're like, wait, light's a wave, right? And we know that light is a wave in that the visible that we can see, the red through the violet, exists in a tiny little range of all of the energies of light. Red is toward the lower energy, violet is toward the higher energy. If you keep going past red, you get into infrared, microwave, and eventually radio. Go past violet, you get to ultraviolet, X-rays, and then gamma rays. So this is where my analogy breaks down a little bit. Because when the ball falls from different heights on those stairs, what happens to the sound? What's different about the sound depending on how far the ball falls? Volume. All right, good. So it should get louder. So maybe you're thinking that as my electron falls, it's going to emit bright light if it falls far away, and it's going to, release dim light if it falls only a little way. Except there's two different ways to think about light. While light sometimes behaves like a wave, it is not a wave. Light also sometimes behaves like a particle that is quantized. So light has both a continuous behavior and a quantum behavior. So which is the true nature of light? Neither. Light is whatever light is, and it's a thing that sometimes behaves like a wave and sometimes like a particle. And this is another one where you don't want to go too deep into this quantum rabbit hole, but whether it behaves like one or the other can be changed simply by looking at it. This is the whole Schrodinger's cat, that the cat is both alive and dead until you open the box and look inside. That's strange. So the problem is that that brightness is not what causes is not where you're getting the increased energy. It's color. If your electron falls just a little bit, it's going to release something toward the red end, a low energy photon. If it falls far, it's going to release something toward the violet end, very high energy photon. So in this quantized version of light, the number of photons is the brightness, but each individual photon can have a continuous value of energy associated with it that we call color. All right, if we can start passing out the glasses now. So if I really wanted to make this analogy with sound and stairs and going up and down stairs a little more like it actually is with light, we could maybe have some fun with something like this. So in this case, instead of saying the sound is louder, we can actually talk about the sound having a different pitch as you go up and down these steps. By the way, this was an actual experiment that was done, I think in Sweden, where they were trying to see if they could get more people to take the stairs and therefore be more active if they made the stairs fun. 66% more people than usual chose to use the stairs when they installed this. So now we have to imagine a stairway where the stairs were different heights and steps that were far apart from each other made very high-pitched noise, and the steps that were close together made very low-pitched noise. All right, enough of that. So this gets even more complicated, but the main thing again is over here. Again, the color is what's going to change. So this is for just a simple little hydrogen atom. All right, we got one proton in the center, and this is all of the fun things that the one electron orbiting it can do. If you're falling down to the lowest level, those are all very big drops, and therefore high energy photons are released. So all of that color is in the ultraviolet range, and they call it the Lineman series. Then we have the Paschen series. This is everything falling to the third level, and these are so short that they're low energy, they're in the infrared. But right in between them is the famous Balmer series, where the lengths falling to the second level are just right to fall into the visible range of what our eyes can see. And so those Balmer lines are extremely important in astronomy because, after all, we now know that, thanks to Cecilia Payne, most of the universe is made of hydrogen. So if you've ever seen someone have like galaxy hair, seen pictures of galaxies, they tend to be like these blues and pinks and purples and stuff. You're going to see why, because that's from the Balmer series. So if you can excite a gas. Remember we said electrons get excited when you put energy in. So you're going to send, in this case, this demo we're going to do, electricity into the gas. You're going to pump up those electrons, but then they're going to fall back down and release light, specifically of the colors corresponding to how far they drop, which shells they drop between. And so for hydrogen, it looks like this. So again, those are the Balmer series, and those are colors that we tend to think of in spacey pictures. Now, planetary nebula, if you look at those, they're typically a lot more colorful, and that's because they have a lot of stuff other than hydrogen in them, so they can have more colors. The second most abundant thing in the universe, helium, has a somewhat similar pattern, except for one rather stark difference, and that's that yellow line right there. And then you can have completely different patterns like neon. If you've ever thought of like a neon sign, they can come in all colors now, but when they first came out, they all had a very characteristic red color, and they were all with neon in them. That's how they got their name, and we can see why they had that red color. So this is one of the key things when people ask me, like, how do we know what stuff out there is made of that we haven't touched, we haven't brought into a lab? This is how. We are literally sniffing the universe with color. That's what we do. So now you're going to get a chance to do this. So activity time. All right, so I have up here a lamp, and I will bring it forward, and I've got 3 different tubes for us to look at. And your job is to try and be an astronomer and tell me what is in the tube, even though you can't touch the tube, you can't analyze the tube in a lab, you're only allowed to look. So with those glasses you have on, when you put them on, if you look up at these lights, you're going to see like a rainbow to either side of the light. Right? There's a rainbow to the left and a rainbow to the right. That's where you're going to want to look. So sometimes it's like you don't want to look straight ahead. You want to kind of give it a bit of a side eye and kind of look off to the side. And so I've decided that you're going to try and guess what's in the tube. All right, can we turn the lights all the way out? Let's have fun in the dark. All right. Now I can only leave the lamp on for a few seconds at a time, or it gets too hot, so are we ready? So there's the color it has without the glasses, which is a nice red glow, and then there's the color you see with the glasses. All right. Don't need the lights back on, we can leave them dark. What do we think that was? Neon. Helium, yeah. All right, shall we give it one more try? Okay, we're hearing more consensus that it's neon. Indeed, that is neon. Good job. All right, you're smart. Okay, now let's try another tube. Okay, so one cool thing to see is to pay attention to the difference between the color you see just straight with your eye versus the color that you're going to see with the spectrum. Are you ready? So keeping in mind, again, let's be smart about this, there's only 2 more choices left. And as we pointed out, there is a very noticeable difference between helium and hydrogen. Make your life easy. You're not sitting here measuring every single line. You're just looking for the patterns, so you know what to look for. All right. You're catching on. Helium. Very good. Now you might say, well, now we know what the last one is. But it's still cool to see it. But what you're noticing here is that first picture I showed when I introduced them is a very idealized version. Real life is messy, which is why I use things like this. All right, are we ready to try and see hydrogen? It's kind of hard, but it's got a pretty purpley pink color to it, though I like it. So yeah, what you're seeing there is also it's not a pure gas in there. They try and make it pure hydrogen, but these do kind of leak over time, and every once in a while I do have to replace them because there's just too much contamination that's got in there. But all right, very good. So this is a huge part of how we know what we know about the universe is rainbows, basically, and thus the outfit I chose for tonight. All right. So now we've got everything down about the tiny, small stuff. How are we doing so far? Do we have any burning questions about something you're like, wait, I really want to know this, or I didn't get this part? We're all good? Yeah?
Is the energy that makes them go to the next shell, is that all light?
It doesn't have to be. In this case, it was electrical energy that was put in. But out in space, yes, you're primarily being excited by light and then de-exciting and releasing light. So there's an absorption and an emission of light, which we'll talk a little bit more here in a second. But yes, you can excite it with other energy sources than light. But the atom is only going to give off light when it de-excites. It only knows one way to do that. That was a good question. All right, so now we're going to do the thing where we skip right over my usual wheelhouse, and we're going to use the small stuff to measure the big stuff. All right, so absorption versus emission spectra. One possibility you can have out in space is this kind of diffuse cloud. We call it a nebula. And if that's being excited by just light coming from surrounding stars, it's going to excite and then it's going to release in the same way you saw in those tubes. And you're only going to see the lines. You're going to see a mostly black background with specific colors being shown as that gas is de-exciting. But you can also have a light source that is what we call a black body. It doesn't really have much to do with being black, but it's basically anything that is solid or at least dense tends to behave like a black body, which means it absorbs and emits perfectly. Of course, nothing does it perfectly, but you can have a light source that's giving off pretty much a full rainbow in an idealistic version of this. Now, if you stick your gas cloud between the light source and your detector, you see a missing color, because all colors are coming through that cloud, but the cloud is snatching up the colors that it can use. And then it's re-emitting them, but it's re-emitting them in all directions, not just the direction to the detector. So most of the light from that light source is just going straight through the cloud to your detector. But every once in a while, that color that that gas cloud loves gets in there, gets absorbed, and then gets re-emitted in some random direction, and therefore it shows up as missing in the spectrum. That's called an absorption spectrum. So they're inverses of each other. Both of them can tell you what something is made of by looking at these fingerprints that every single atom, every single molecule has. But which one you're looking at depends on whether you're looking at a cloud giving off like these lamps, or if you've got a background source and it's passing through a cloud and you're losing that color. All right, so why does sunlight make a rainbow instead of just a bright hydrogen-helium emission spectrum? Right? We know the sun is mostly hydrogen and helium. So what we actually see, this is a very stretched out spectrum of the sun, starting from near infrared and running all the way through to the violet. So every single one of those dark lines is an absorption line. And that's because the sun is very dense. So the light that's coming from the nuclear fusion inside the sun is coming out at all wavelengths. But then it passes through the thinner atmosphere of the sun. And that's where it starts to gobble up the specific colors that everything in the atmosphere likes. And so this, again, was Cecilia Payne's job of looking at this and realizing that the sun's spectrum was telling you what the sun was made of, and revealing that you can see a few very notable lines, like there's that hydrogen Balmer, there's that cyan Balmer, then there's a few more down here. Here in the yellow, one of these yellows is probably that strong helium line as well. So you can start to kind of see where she was going with this. Now let's talk about the Doppler effect. This is something that we've probably all experienced in everyday life. It's a sound effect, so let's hear it. Lay on the horn. All right, we've all heard that, right? Okay, so there's two different statements that I've seen used to describe this. Only one of them is correct. One is the pitch goes up as the source approaches and then goes down as it passes and moves away. Or the pitch is higher as the source approaches and then decreases as it passes and stays lower as it moves away. So can we listen to it one more time? Which of those two do you think it was? Number one or number two? Vote for number one. Vote for number two. Very good, number two. So yeah, a lot of people mistakenly think that the pitch should be rising as the car is approaching. But what's actually rising is the volume. So this gets right back to that confusion of, well, what do you mean by light's energy? Do you mean how bright it is or what color it is? So no, the pitch is at its max as it's approaching and then dips down and then stays low. This is similar to the language issue where you ask someone, are days shorter, do days grow shorter in the winter and longer in the summer? And most people go, yeah, that sounds right. And you're like, absolutely not. Days grow longer in the winter and grow shorter in the summer. Because the start of summer is the solstice, the longest day. So as summer progresses, the days are just getting shorter. And the first day of winter is the winter solstice, the shortest day of the year, which means winter is just days getting longer. The mess up here is that what you meant to say is that days are shorter in the winter and longer in the summer, simply because winter you're coming out from the very low end, and in summer you're coming down off the very high end. But this is a semantics issue. So what causes the Doppler effect? Well, if you're just sitting still releasing sound, it kind of goes out away from you like ripples on a pond. But if you're moving, those ripples get asymmetric. And they tend to crunch up in the direction you're moving. So if you're standing here, that's why you're hearing this high pitch that's actually, yes, higher than the actual pitch of the sound. As it passes you, you briefly hear the actual pitch, and then as it moves away, you're hearing a lower pitch because they're all stretched out. Now, I tried to find a lot of videos that kind of showed this in action, and I thought all of them moved way too fast. So I just dove in there with PowerPoint and made my own version that we can go through nice and slowly. So here is our sound source. It releases a sound wave. Very nice. That sound wave expands. So the colors are important. That red sound wave is going to always be expanding away from the position of the red dot. Nothing can change it now. It's left. So what happens if the dot then moves to the orange position and releases a new sound wave? And then those two expand, the red from the red position and the orange from the orange position. And then the dot moves again and releases another sound. And then those all expand, and then it moves again and releases another sound wave. So this is what's happening. Each sound wave, as it is released, can now only expand away from the position from where it was released. It can't stay and keep up with the object that's moving that made the sound. This is how we are able to break the sound barrier, because the waves just can't keep up and you can go and exceed their speed. All right, so that's the Doppler effect. We're good with sound. But hey, sound and light are both waves. Well, light's kind of a wave, but not really. But sound is definitely a wave. Sound is definitely a wave. And light is kind of like a wave. All right, so wavelengths of sound, right? The wavelength, a wave is something where something is oscillating. It's going up and down. And the length can tell you how low or high the pitch is. So the long wavelength, this is like 3 football fields. That's a very low tone outside of what we can hear. We move to wavelengths that are more like tall building. That's where whales start to be able to hear it. We get down to something on the order of maybe this floor to ceiling distance. Now we're in the range humans can hear. This is about a foot. And then we get down to a little over an inch. Now bats are able to hear it. And we leave the human and whale range. And now we're into millimeters, so like little pinch. And then medical ultrasound gets up here into teeny, teeny, teeny little wavelengths that are very high energy. And what's also fun, of course, is that what tones you can hear changes as you age. I've gotten to the age now where they do those experiments, like how high of tones can you hear? And it gets to a point where my kids are like, yep, we can hear it. And I'm like, I hear nothing. Lots of rock music. I don't regret it. So what about light? Well, light, when it's behaving like a wave, also has wavelengths of different sizes, though the spectrum is far more extreme. So you start out with radio, and that's like the size of buildings. All right. And then eventually, as you're transitioning from radio to microwave, you're on something of the order of us. And then as you get deep into the microwave, now you've got a wavelength that's about the size of an ant. As you pass into the infrared, you start getting things on the order of the eye of a needle. And then as you're about to get into near infrared and red, you're at the size of a protozoa, so single-cell life form. Very quickly, you pass through our visible range, because it's just a teeny tiny part of the spectrum. And now you're into the size of viruses as you're entering the ultraviolet. You get toward the edge of the ultraviolet to the X-ray, you're in the size of proteins, so very large molecules. Then solidly into the X-rays, you're down to wavelengths the size of an atom, and then gamma rays, a wavelength the size of an atomic nucleus. Again, when it's behaving like a wave. If it's behaving like a particle called a photon, then each photon has an energy associated with one of these colors. So this gives us a way to measure how things are moving using light. So if you have a galaxy that is moving toward us, the waves ahead are getting smooshed, and we know that that means bluer. And so on Earth, that light would look bluer than it actually is. But then if that galaxy starts to move away from us, now the waves are getting stretched out, so they're being more red than the light actually is as it's moving away from us. Now, an important question you might ask is, well, that's all well and good, but what if I don't know what color the galaxy actually is? Fair point. How do I know that I'm not just looking at a particularly reddish or bluish galaxy? How do I know that that color is from movement and not just the color of the object? Spectra. Those lines, those fingerprints, are immovable. They have to happen where they happen. And so if these are the Balmer lines when you're just measuring something in the lab or the lamp that's not moving, they look like this. But if you have an object that's moving away from you, those lines all shift toward the red end a little bit. They should not be there. There is no element for which that is the actual spectra. It's hydrogen that is red shifted, we say. It's moving away from us. Likewise, if it's moving toward us, all of those lines will be nudged slightly toward the blue end. So you're right, we don't necessarily know off the top of our heads what the color of the object actually is, but we definitely know where those lines should be. And so if those lines are off, then we know that it's moving. And which direction tells us which direction it's moving, and how far it's shifted tells us how fast. The faster something is moving, the more those lines are going to shift. So this gives us a way to measure speeds of things in this big stuff realm. Stars, nebulae, galaxies. Okay. So now let's talk about that big stuff. how do you measure cosmic distances? How do you go out there and know how far away something is? The night sky just kind of looks like everything's the same distance away. Depends on how far away you're trying to make the measurement. So we're going to do kind of a little stepping stone here. Our first step is the very simple stellar parallax. You get to have an activity time, but this one is really easy. You just need a thumbs up. You just put your thumb out in front of you, and if you can wink, you can close one eye, or you can simply cover one eye and then just do it back and forth. If you flip back and forth, you'll notice that your thumb seems to be jumping back and forth with respect to the back of the wall or the screen. That's parallax. You have two eyes, and those two eyes are seeing the thumb, but then continuing on to different locations. We can do the same thing with stars that are close to us. The Earth is like a giant eyeball when it's on this side of the sun versus this side of the sun. These are like your two eyes. And a nearby star is going to be seen in this area. So seen from B, you can see these two stars and these three stars, 1, 2, 3, it's going to appear right in that area. But when we're at position A, now it's going to look like it's hanging out with these two stars and not these three, so now it shows up over here. So by looking at stars very carefully and finding that there are a few stars in the sky that noticeably seem to change their position with respect to most of the other stars in the sky, we know that those are rather close stars, and by measuring how much that shift is, we know that angle, and therefore we know how far apart it is. So this is our first stepping stone, is to look at nearby stars and look for parallax. Look for the difference, winter versus summer, of where that star shifts a little bit with respect to stars that are really far away. All right, next stepping stone is that we have learned about the different types of stars. You can't just have a star that's any color and any brightness that you want. Stars are governed by the laws of physics, just like everything, and so they are confined to only doing a certain number of things. So two main features of a star, one is how hot it is, and keep in mind, like, red means cool in space, and blue means hot. And then there's how bright the star is. And this is given in terms of the sun. So 1 is the same brightness of the sun. 10 to the second, that's 100 times brighter than the sun. 10,000 times brighter, 1,000,000 times brighter. And to the other end, 1/100th is bright, and 1/10,000th is bright. So we've got temperature on one axis and brightness on the other. But these are the what we call absolute magnitude. They are how bright that star actually is. But we all know that how bright something is depends on how far away it is from you, right? So if things really close, it's going to look brighter than if it's farther away. So this becomes a way that we can judge distances. If we know how bright a star should be, and we know how bright it looks to us, then we can work out the distance. So a nice, easy thing to measure is the color of a star to find out its temperature. So for instance, if I find that, like, ooh, it's this really cool star down here, then I go over here and I know that's a red dwarf, very low luminosity, and I can work out therefore the distance to it. The sun is right in here at 1 and about 5,000 degrees. This is why it's called a yellow dwarf. It's not actually yellow, it's just that it falls in that temperature range. Sunlight is white. The color of fresh snow is basically sunlight. Now, you might be asking, if you're like, wait a second, if I know the temperature, how do I know the difference between, say, a red dwarf or a giant or a supergiant? How do I know the difference if it's a blue star between a white dwarf and a massive main sequence star? The main sequence is where most stars spend their life. When they die, they move off into the giant realm and then either blow up or, like the sun, drift back down to white dwarfs. Not important, but the question arises, if all I know is the color, how do I know what region it's in? Thankfully, the spectra, even though they give the same lines, the lines look different depending on what kind of object you're looking at. A blue giant star is got an outer layer that's very diffuse, right? It's passing through an atmosphere, so those lines are nice and sharp. But a really dense object like a white dwarf, the lines get spread out more. So by looking at the shape of the lines and how defined or diffuse they are, can tell us then the obvious difference between a giant star and a white dwarf, or a supergiant and a red dwarf. So there's more information than just where the lines are. There's also what the lines look like. All right, so this is nice. We got the distance here. If we know the temperature, we know how bright it should be, we know what type of star it is, then we know how far away it must be based on how bright it looks to us. But what about moving beyond that? What happens when you can't see individual stars anymore, like if you look at other galaxies? Well, thankfully, we had a very smart person, Henrietta Swan Leavitt, that noticed that certain stars tended to brighten and dim very regularly. And these were called Cepheid variables. And that you could measure the change in that brightness over time, and it was very regular. And most of them had periods on the order of days. So this one has a period of 9 days over which the star brightens and dims. And what she noticed was that there is a very strong correlation between that period and the brightness of the star. And there's two different types of Cepheids. Don't worry too much about them. But here we have the period, the length of this oscillation in days. And if I say measure one that has an oscillation of 20 days, and I know it's a classical Cepheid, I follow that up here. I'm here, and now I look over here, and that tells me how bright that Cepheid variable is. And now I'm right back to, if I know how bright it is, then I know how far away it is because I can measure how bright it looks to me. So this is a great thing, what we called a standard candle, is what we call it. Something that we know for sure how bright it is, and therefore we can always be certain of how far away it is. This was also the discovery that led to the realization that these fuzzy small clouds out there were not nebulae, they were other galaxies. This was the realization that the Milky Way was not the entire universe, because when people started to find these Cepheids, they found some that were clearly way farther away than any other star they had seen. The Milky Way is 100,000 light years across, but the Andromeda Galaxy, the closest large galaxy, is 2.2 million light years away. So this was one of those points of expanding our definition of the universe, realizing that the Milky Way is one galaxy of many. And also then helping us to understand what the Milky Way actually looks like, because that's hard to tell when we're inside of it. All right, now the Andromeda Galaxy, if you've had a chance to see it, it doesn't look too impressive. This is a pretty dark sky and a fairly long exposure, and still it's just this little wisp. I think once I've convinced myself I could see it with the naked eye, and it's just like this little faint cigar. And the key to seeing faint things like that in space, because I learned this when I went down to Australia and tried to see the Magellanic Clouds, don't look directly at it. Look off to the side, because your peripheral vision is not good at color, but it's really good at brightness. And so look off from where you know it is. And one time I did convince myself that I saw it. However, this is not because the Andromeda Galaxy is that small to us, it's just that it's that faint. If we could see the entire Andromeda Galaxy, if it was bright enough but still the same distance, it would actually look this large in the sky. So we're only seeing like the very little center part, the brightest part, when you look at it with the naked eye or even through pretty modest telescope. It's huge. So now we've managed to get to where we can tell the distances to other galaxies. But at some point they get so far away that we can't pick out those Cepheid variables anymore. So what's next? Well, then it's time to talk about the biggest stuff. And we'll start with the Hubble Ultra Deep Field. So the Hubble Space Telescope picked an area of space that had virtually no stars in it from the Milky Way. I think I've counted there are 3. There's this one, and this one. And I didn't see any other stars in this image, which means every other single smudge and dot in that image is a galaxy. 10,000-ish in this one image. It took Hubble 23 days of staring at this spot to make this picture. 23-day exposure. So, how deep is the ultra-deep field? Let's try and do a pan out, appreciate just how deep this is. So that's the extent of the ultra-deep field. Now we're coming out to the extent of the deep field. Now we're starting to see a lot of stars of the Milky Way. And now we're kind of losing track of that ultra-deep field. Starting to see the brighter stars of the Milky Way. And there. But now you might be saying, like, yeah, but how big is that part of the sky? Fair. Another way you can picture how big of a piece of the sky that was, a tennis ball. Place it at one end zone of a football field, and you stand at the other end zone. That's the size of the ultra-deep field on the sky. A tennis ball at 100 meters away. All right, well, you might know that scientists back in 1929 started to notice something very interesting about looking at galaxies, in that some of them, especially as they seem to be farther and farther, also were redder and redder. They knew about the Doppler effect. They said this could be a really cool way to measure the distances to galaxies, but they noticed there weren't any blue ones. They were all red once you got beyond a certain distance. The Milky Way and the Andromeda Galaxy are actually heading toward each other. In about 5 billion years, they're going to collide. It's going to be magnificent. No stars are not going to crash into each other. Space is mostly empty, but it is going to totally mess up both of their spiral structures. It's going to be awesome. Unfortunately, the sun will be dying at that point, so we won't be around to see it. But when you start looking out beyond just a local group of galaxies, they're all moving away in all directions. And as you look further and further out, they just look redder and redder. Until it's pretty obvious that they're redshifted, because you just expect a galaxy to have somewhat white light overall, and they're obviously red. Now you also may know that the farther away you look, the farther back in time you're looking. So there was also the discovery that not only is everything moving away, is the universe expanding, but it's also expanding faster and faster. So we have here kind of that history of the universe. The Big Bang is whatever happened at the beginning. If there was a beginning, we actually don't know. The Big Bang theory just allows us to keep on moving further, further, and back in time, closer and closer to what seems to be a point of beginning. But honestly, we don't yet know. What I find really interesting was that in Einstein's time, the overall thinking of the men of science, and women, but men of science, was that the universe is static, right? It's all kind of moving around and changing, but overall, it's always been here, and it always will be here, and nothing is really going to change. They actually didn't like the idea of anything else, because that started feeling like creationism to them. They're like, I don't like that. We're scientists. We're not religious. So it took a Catholic priest who is also an astronomer to really kind of put everything together and say, hold on, I really do think that if everything's expanding, if we run the clock backward, it seemed like everything started at the same place. And other scientists thought this was ridiculous, and so the word Big Bang Theory was actually mocking him by calling it that. It was like, how stupid is that? Just a big bang started the whole universe? And the name stuck. So, little pitch for having a diversity of thought in your science group, because somebody might see something and interpret it in a way that you just didn't want to. So, looking farther and farther in space, we can look further and further back in time. But there are a few problems that we run into. Right after the Big Bang, everything was highly dense and very hot. But it was also very dark. You might say, what? It was super energetic. It should be bright. No, it was dark, because it was so dense that light just really couldn't travel any amount of appreciable distance before it was reabsorbed, and then travel and reabsorb. It'd be like sitting inside a chunk of lead. You're not going to see anything even if there's all sorts of energy running around in that lead. It's just too dense. All right, eventually things calm down enough, and then we enter what's called the Dark Ages. So there are actually two Dark Ages here. After things calm down, you've got that Dark Age, and then you finally get enough room to have things like protons and electrons. Now they're flying all around, but still not doing much. But then it cools down just enough that some of those protons and electrons lose enough energy and are moving slow enough that the protons can start to grab the electrons, but only for a second, and they lose it again. I'll get the next one. And so they're trying, but the electrons are still too energetic. And then finally, there's a moment where the electrons start to just give up and fall toward the protons, forming the first atoms. And all of this cascading down causes a sudden glow to fill the otherwise dark universe. So remember, helium and hydrogen, right? They fall down and create all of those beautiful lines. And if you mix those together in the right amounts, you basically kind of get this yellowish orangish glow. So there was this moment when suddenly the universe was just awash in this orange glow from the first atoms being able to form. The electrons finally giving up and falling in and becoming bound by the protons. And then everything kind of went dark again because there were no stars. So we had to wait for a while, for about 400 million years, for stars to form and for light to enter the universe again. So one of the dark ages is because it actually was dark. But there's another dark age in that we can't see beyond a certain point if that red shifting goes all the way out of the visible range. So Hubble can only see so far. Hubble sees mostly in the visible range like our eyes. But once everything red shifts so far that it leaves that visible range, dark. JWST sees in the infrared. So JWST can see farther back in time and farther away than Hubble can because it can see things that have red shifted all the way past red into the infrared. So JWST is not just that it's bigger, but it also can detect things farther away that have just gone red beyond red into the infrared. So what about this orange glow? It didn't just disappear. Those photons that were created just kind of mingled about in the universe, and some of them would get absorbed and then re-emitted. But some of them just continued to float around. And as the universe expanded, that orange wavelength just kept on getting stretched and stretched. As they were traveling through an expanding universe, they were being stretched out like an elastic band until their wavelengths got longer and longer and longer and longer. And a few of them are still around. We know this because when people started doing radio astronomy, they found this really annoying thing. It was this background noise everywhere. No matter which direction you pointed your telescope, it was this faint static. For a while they couldn't figure out, like, why is there just this buzz, this background noise everywhere? And then they put two and two together. And they realized that from that moment of that orange flash of the first atoms forming, over the entirety of the universe expanding, that what photons remained had survived from that they were so stretched out that they had entered beyond infrared way deep into the microwave and radio range. The cosmic microwave background. Now, this is one where I get to say, like, I was wrong. And I'm glad that I was wrong because I get the exciting thing of realizing I was wrong and then knowing something even better. I often thought of the cosmic microwave background as just that, a background that was out there in space. You often hear it described as the leftover glow from the Big Bang, which it actually isn't. It's from that period when, after the Big Bang and atoms first formed, but still, a glow from there. So I always pictured it as something far, far away. But it's not, because it's not an object, it's light. And if we're picking it up, that means it's here. The Big Bang happened everywhere, including right here where we are. And that orange glow filled the whole universe, everywhere, including where we are right now. And those orange photons are still floating around, stretched way out into the microwave and radio range, are still hanging out here. We're in it. The cosmic microwave background is here in this room with us. It's everywhere. Some of those photons from that first glow of the universe are still bouncing around with us in here. And that is kind of where I leave you at the biggest overall structure of the universe itself, with those tiny variations that quantum physics people are trying to figure out what that might mean for why it isn't perfectly uniform, but has some higher and lower parts. But that's where we're going to stop for today. I'll take questions.
I have a question.
Yes?
Isn't the Big Bang still happening? Like, it never stopped. It's still, and it wasn't like, it didn't happen in space. It actually created space.
Yes.
So it's still creating space.
Yes. So the question is, isn't the Big Bang still happening? Because if the Big Bang created space and this is all space, then we're still sitting here in the Big Bang.
And it's expanding.
And it's expanding. And yes, you could look at it that way, right? The Big Bang, instead of looking at it as a moment, you're choosing to see it as a process, which is what people are starting to think. Instead of trying to elusively get back to this point, that maybe just didn't, you can keep on asymptotically getting smaller and smaller and smaller, but also never get to an actual point you started at. So I like that you're thinking of it as a process that, yes, is ongoing because everything is still expanding. And where did the Big Bang happen? Here, there, everywhere. All of this. Good way of thinking about it.
Any other questions? Hold on, I'm going to put you on so that the people on the live stream can hear you.
I was just wondering, you talked about the color of light that emitted if it was moving away from us or towards us. What color is if it's running like parallel with us?
So if it's moving, but it's not moving relative to us, then you would see no shift in the color. It would look its true color, basically.
Almost like it was standing still.
Right. So yeah, if there was literally no movement, or at that moment that you're passing each other and you looked, yeah, you'd see no blue or red shift. You'd see the true color.
Although
Yeah.
ultimately, I mean, it's not like things are just moving completely in that direction away from us versus, so if it's moving in that direction, it does have a shift. It's just not as fast as
Right,
it
you got
would
the
be had it
angle,
been
like,
straight away from us, as
right.
it were.
Yeah.
And that's why when you hear the Doppler effect, the most dramatic change happens as it's passing you, because that's when that angle is changing the fastest. This is not really changing the angle it is from me, but this changes really fast, and then it's like moving very slowly. So that's why that dip happens so dramatically as it's passing you.
And just sort of to add on to the Doppler shift, you had asked the question, why isn't it, as it's coming to you, getting higher in frequency as time goes on? Where it does get higher is depending on the speed.
Right.
So if the car is traveling at 40 miles an hour, that shift would be, a certain frequency. But if it's traveling at 80 miles an hour, it's going to be much higher in frequency. And so that can help tell us about how fast something is moving away or toward us.
Right. You could get the pitch to go up as it approached if the car was accelerating as it was approaching you.
That
Because
too.
then the speed would be getting higher, and that would be crunching the sound waves even more. And so, yes, that car was traveling, I assume, at a constant velocity. But yes, an accelerating car, you would hear the pitch going up.
Any other questions? Oh, another one back here. Okay.
I've heard that the Big Bang started from a singularity. Can you define what a singularity is?
Whew. Again, you're pushing me outside my wheelhouse. I do have a degree in astrophysics, but I've been embedded in solar system studies for a long time here. A singularity is a hypothetical idea. It's kind of like infinity. Infinity is not a number, it's an idea. A singularity is the idea of everything just being infinite density all space being crunched together. However, I think this creates a bit of a stretch because people think of singularities with black holes as well. But again, we don't know that there's a singularity inside a black hole because we can't see what's inside a black hole. Physics as we know it seems to say that there is, but also completely breaks down once you try to look inside the black hole. So people start to think of the Big Bang as like, oh, it was this point, like what you think is at the center of a black hole, and it did that. But it didn't, because that would require space for it to expand into. It is space. And so asking, like, where did it happen? Again, everywhere. All of this was in that singularity. And that's where your brain might break a bit, and that's fine. It's normal. But yeah, it breaks mine too. But if I can give you something that will smooth over that break. One idea, and it's just an idea, is that if the beginning of the universe was defined by a singularity, and if a singularity is also what happens inside a black hole, and if the multiverse is a thing, perhaps a black hole forming in one universe is what gives birth to another universe. What if the singularity in a black hole like literally pokes itself out of that reality in existence, and that's what creates another universe? So what does it look like in a black hole? Might be this.
All right, we do have a question from the chat,
Yeah.
from the YouTube chat. This is, do photons interact with anything as they travel from the Big Bang to current time?
Yes. So a lot of them, yes, will encounter atoms. They'll get absorbed and re-emitted. But keep in mind that that reabsorb and emit cannot change the color of the light, the energy that it has, right? Electron takes, electron giveth back. So even though that light might be absorbed and emitted repeatedly, it still is almost as if it's the same photon, because it does have exactly the same energy and all the properties that the photon had going in, the photon coming out does.
Sort of a Newton's cradle of...
Yeah, exactly. And so there's some people that say that, you know, you really should still even think of that as the actual same photon that just happened to wink out of existence and wink back into existence after that. So yes, those photons of the cosmic microwave background have interacted with matter, but they have not done so in like a way that would alter their color. So they're still just all hanging out there.
All right, any other questions? Oh, another back. Okay, hold on a second.
The expanding universe. So as the universe is expanding, the galaxies will spread apart again, and then will we have like another dark age? Like, is it going to get dark again, you know, from everything spreading out like
Yes. Unfortunately, that seems to be, if everything we know points to a future that is very bleak, in that as things drift farther and farther away, and you know, black holes eventually dissolve through Hawking radiation, white dwarfs finally cool down to absolute zero, that we are heading toward this time where the universe will be completely dark and cold because everything will just expand too far. There's also an idea I've heard floated that space does have a breaking point, that you can't keep stretching it infinitely, and at some point it will just rip out of existence. Really don't know. But yeah, the natural progression of this is indeed a place that is just, everything is far apart, everything has dissolved, and everything's at 0 degrees Kelvin, and no more light is being made.
Hopefully that rip will happen a long time from now. All right, unless there's, I'll get another question back here, hold on.
Is there any way to measure how much energy is in the universe?
Ooh. So no, because we don't actually know how big the universe is. Keep in mind that as we're looking farther out, we're looking farther back in time. If the universe has a fixed age, that also means there's a fixed distance we can never see beyond, because the universe has not been around long enough for light to have reached us from those locations. Now that's not just 13 billion light years away, it's much farther because the universe has been expanding all this time, but still, we are certain that there's likely parts of the universe that we just have not yet seen because the light's so far away that the universe hasn't been there long enough for the light to reach us. This also happened in like the short time right after the Big Bang. There was this great inflation where the universe just went like really fast. Like space somehow expanded faster than the speed of light. Do not ask me to explain that. I don't even fully get it. But yes, so there's likely universe beyond that. So we could make this vast estimate of the total energy of the visible universe. But as far as the actual universe, we don't even know.
All right, well, Zoe, I want to thank you once again for an outstanding presentation.
Thank you.
I just let you know that literally people from around the world, Raving Ray wrote earlier and says, good morning, 8 a.m. from Manila, Philippines,
Ooh,
watching, doing household chores.
nice.
So anyway, we do have people from literally around the world that do plug into this, and again, we invite you to go to our YouTube channel to check out some of our previous ones. Next week next 2 weeks will be Robot Week, if you will. We've got a group from Seton Catholic Central that have a sort of a Lego-based robot that they are going to be presenting. And then the weekend after that, the Southern Tier Robotics, who are basically, this is probably about their 8th or 9th presentation. They come up here. They have these robots, competition robots that are probably about 3 foot by 3 foot by sometimes 4 foot tall, that they've taken to competitions. And these are high school students that are bringing it. So you definitely want to come and check that out as well. And then the week after that, we'll be talking about the Galapagos Islands and why it's so unique. So look forward to having you come back. For those of you who did come in and pay, well, we have a rule here that says you can't leave until you look through a telescope. Unfortunately, tonight is not your night. So what we will do, however, is if you did pay, see me at the cash register, and we'll get you a card to come back on another night, hopefully one that is a little better for viewing. But again, every Friday night, we always have something compelling to come back for. And thanks again, Zoe, for coming down from Cornell. And look forward to seeing you all soon.
Thank you very much, everyone.